so thank you. So that's I will talk about non-commutative sort of Catalan numbers. Well, which is actually not numbers, but rather Laurent polynomials. I will explain this. And so this is a joint paper with Arkady Berenstein from Oregon. And actually, so when we started to do this, to discuss on this subject, we were basically interested in three topics. First, in applications sort of Laurent so-called Laurent polynomials. Next, well, also in solutions of non-commutative quadratic equations. I will mention this. And the third topic was actually we were interested in properties of Hankel matrices with non-commutative entries. Okay, but so let me just start. So if I have time, I will also talk about non-commutative binomial coefficients, whatever the byproducts of this. Now, there's I don't know, 1,000 definitions of Catalan numbers. I don't know, I need only 3 right now. And so that's classic definitions. And so they're described like this. One is sort of, you have just coordinate plane with an integer or integer coordinates, and then you consider it a path from the origin into just a point n, and so you count all passes which are sort of such that you go to the right or up, but not above the diagonal. So you consider counting passes like this. So on. And so the number is a Catalan number. That's one definition. Another one definition is sort of recurrence relation. And so you put C naught equals 1, and then you define numbers given by the following recursive relation. So that's sort of another definition, which can be translated into the relations for generating series like this. You consider a generating function C of t. T is a set such that it's like this, and so on. Then this relation became the relation of t. C equals 1 plus t C of t squared. So that's just another way to write this. And then there is just definition through Hankel determinants. And it says that just for any n, so this the determinant of Hankel matrices. So this is C2n is 1, and the same if you start with a And I will sort of try to generalize all.
So that's definition of commutative.
That's actually definition.
Oh, so
if you put zero equals 1, which is also yes, then that's, and if you have this, and then you have properties of this. And to be honest, at first we started with understanding this definition, but that's anyway. Okay, now so just let me define, let me then start with the non-commutative analogs. And so first of all, I will start with this. So suppose I have an infinite set of free variables. So x0, x1, x2, so on. Those are just free variables, and I will denote Fn. It's just a free group. With generators. Again, x1, x2, xn, and I may include actually all. Just f will be just f infinity, so this is when all these sequences are. Okay, so if you have a free group, if you have any group, you may consider so the group ring, which is just linear combinations of elements from this with the integers. And let me just use construct the standard homomorphism, which actually defines that xi is 1 actually for all. And I need this actually to compare my definition with the classical. Okay, so let me just introduce then. Should I go? Maybe I will go here. Let's see again. And now let me introduce so just Laurent polynomials, which I will denote C of x. I would prefer actually to write this just as a script C, but on the blackboard it's better to do this. And so I will do so the following. And so given a path like this, so just 20 paths. Construct Laurent monomial MP by the following rule. First of all, I will consider all angles, so like this angles. Now, angles are given, say, by coordinates, say, ij. And so training coordinates ij corresponds so just an integer which is denoted cij, and this is I. The definition is I minus j. So that's a standard notion which is called content in McDonald's. So it's McDonald's book, so that's this. So if A so has coordinates ij, I will write C of A instead of C of ij. And now I will denote, I will define M.
So why is it angle and not the vertex? Ij.
Ij would be just, it's all possible angles.
But we can also talk about vertices. About points. Well, why do you talk about angles? Is it easier? Why you need it?
I need only angles.
Oh, okay. So 1, 0 will not be perfect.
I need only on the angles, so those I don't count those.
Yeah.
Okay, so now let me just define MP. It's just a product for all possible angles. Of x's, x, well, I read this, x are three variables. The index is C of A. And here I have to put just a number, it's called. And signum of A is equal to 1 if I have an angle like this. And -1 if I have an angle like this. So, and I will define Cn of x, definition, as sum of MP. And so just MP, just all possible passes from this 0, 0 to n. Oh, satisfying. So let's talk about examples. Let's see how let's talk about examples. So C naught of x is just x naught, so that's, okay, consider this just as a convention. C1 of x, so I have to just to go from 0, 0 to 1, 1. There is only one pass. And so that's the angle. This angle is 1, 0. So the quantity is 1, so that's x1. Okay, now so let's do so the next part. So you have 2. And how you can go from here to here? Well, you can go one way, just from here to here. You have to jump. And this is 2, 0. It corresponds to x2. And another one is that you go from, well, this is like stairs. So you have like 3 angles. Here, 1, 0, 2, 1, and 1, 1. So to 1, 0, that's x1. Here, 1 minus 1 is x naught, but the angle looks like this. So that's -1. The next is 2 minus 1, x1. So C2 of x is x2 plus x1, x0 minus 1, x1. And I will do C3 as well. What do you do here? I need to kill this. Okay, so that's C3. So this is one goes like this. Oh, I have this red, so maybe that's better to do this. And this is just 3 nodes, so that's X3. Next, I have this. And then next one, I have just, okay, I have then here, 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 and here. So, and here I have x2, x1 minus 1, x2.
Yes.
Wait. Oh, yes. Yeah. Right.
Okay. Then next will be, so this one, this one, this one, and this. And here I have x2, x naught minus 1, x1. So this is, so this guy corresponds to x naught, and with this is just this. Then at Gelfand seminar, I would give this as an exercise to somebody, but then
Yeah.
okay, and then I
I'm
have,
not a student.
all right, let's save time.
Thank you. Yeah.
Okay, so this one, let's see, this is going to be
That's
x1,
x1,
x0 inverse, and
Yes.
x2.
x2 exactly, and just the last one will be, but that's actually easy because that's it's just a standard stair. And to this, it's easy to set sketch box.
X1, X0.
Yes,
X1,
that's x1, x naught inverse, x1, x naught inverse, x1. So you have, I will go here, so you have C3 of x, is just x3 plus x2, x1 minus 1, x2, plus x2, x0 minus 1, x1, plus x1, x0 minus 1, x2, plus x1, x0 minus 1, x1, 0 minus 1, x1. So by construction, of course, you have that that you may consider, but by construction, of course, you have that the stuff is just standard CM. Now, actually, I can give you one more interpretation, maybe here, and so another interesting specialization is defined when xi goes to q I minus 1 over 2. So this is this one. And then Cn of x goes to Cn of q1. And this is in the notations, or actually numbers introduced by Garcia and Hankel. So they actually define Catalan numbers depending on 2 parameters, but we can cover only so far only this stuff. So that's basically so the definition. Now I have to say something about this recurrence relation. define a recurrence relation. So first of all, I need to define a shift. And so T from ZF to ZF is a map, and it's defined just by adding one more to this. Then the relation looks like this. Vortex C and plus 1 of x. And this is sum k from 0 to n. This is ck of x. Then you have to multiply by x naught, that's just this variable. Okay, then you have to take x, but you have to shift. So this is so you take the shift. Of course, if you apply epsilon, then this gives you standard number, that's 1. That's just again Cn minus k. The shift doesn't care. Epsilon doesn't care about it. So this one. So let's maybe consider just an example. Let's take C3 of x and let's compute this. C3 will be equal to C naught x, x naught inverse C, C2 x, x capital, this is x capital, right here, plus C1 x, x naught inverse G, C1 x, plus C2x, x naught inverse G, C naught x. So let's see what. So the right-hand side equals to x naught for C of x naught times x naught inverse. And then shift for C2 would be x3 plus x2, x1 inverse x2. So let's do the next. It will be x1, x naught. Then C1 of x is x1, you shift, you get x2. And so the next you have x2 plus x1, x naught inverse x1, x naught inverse minus 1, C naught is x naught, that's x1. So I will give an exercise to check that this is exactly C3 of x. Now the proof is, of course, it's very simple, but in all this approach, if you have the right definition and the right theorem, then the right decision. Okay, now let's go to generating series. what we have for generating series. So let me just, so I will use maybe tilde in this case, and this will be C naught of x plus, C1 of xt plus C2 x t squared and so on. And t is a central parameter, so t commutes with x's. And so then the quadratic equation written over there looks like C of t equals x naught plus t C of t x naught minus 1 t C of t. So that's no surprise. I would like actually to discuss so I would like actually to discuss an interesting application of this stuff. So let me recall that F1 is a free algebra generated just by x naught x1. And I will define just the homomorphism alpha of f to f1 by formula alpha xk equals x naught k minus 1 x1 to the k, so k greater than 0. And let me set, say, C, well of t will be just x naught times alpha applied to C of t. Okay, and then I have this proposition that C, shouldn't be n here. That's so that C of t is equal to 1 plus t C of t, sorry, x naught